you by thesis123.com. I learn and teach online.
Here's the next question, number 38. The single line diagram of a balanced power system is shown in the figure. The voltage magnitude at the generator internal bus is constant and 1 pu. The pu reactances of different components in the system are also shown in the figure. The infinite bus voltage magnitude is 1 pu. A three-phase fault occurs at the middle of line 2. The ratio of the maximum real power that can be transferred during the pre-fault condition to the maximum real power that can be transferred under fault condition is dash. So here we don't have, it's not a multiple choice question, we have no options, so we will have to try our best and work it out as much as possible. So the question asks us to find out the ratio of the maximum real power that can be transferred during pre-fault condition. So that's power at pre-fault to the maximum real power that can be transferred under faulted condition. Power at faulted condition. This is the ratio that we are asked to find. Alright, so there are a couple of steps, quite a number of steps that go into solving this problem. Let's work it out. First, we need to calculate the maximum power at the pre-fault condition, that is before the fault has taken place. So before the fault has taken place, let's try and resolve this into an equivalent circuit. So when we do that, we see that we can add up these two impedances given, J.1 and 0.5, since they are in series. So that's J.6 for this line, and here it's J.6 as well. Note that the question says that the fault occurs somewhere in the middle of the second line. Okay, so we'll come to that in the second step. So the first step, let's write down. Okay, this is without the fault occurring, or pre-fault. Okay, and this is the equivalent circuit. Let me just draw that. So we have, this is for the first line, this is for the second line. Here we have our infinite bus, grounded. Okay, so we have been given that it's 1 pu here, 0.2 here. We calculated this as 0.6 for the first line, 0.6 as the second line, and the infinite bus is at 1 pu. Okay, so this is our equivalent circuit. If you notice, it has all the components written here. Okay, so let's find out what is the power at pre-fault. At pre-fault condition, now our general power formula in terms of voltage and impedance is V square by Z. So let's use the same thing. We have 1 pu square divided by the resultant of all these three impedances that we have here. Now 0.6 and 0.6 are in parallel, 0.2 is in series to this part. So here Z would be 0.2 plus parallel of these two, which would be 0.6 into 0.6 divided by 0.6 plus 0.6. Now if we are to solve this, 0.6 into 0.6 divided by 0.6 plus 0.6 gives us 0.3. So here Z would be 0.2 plus 0.3, which is 0.5. Substitute that over here, 0.5. 1 by 0.5 gives us a power of pre-fault as 2. So we'll keep this aside. So this is the numerator part of the ratio that we are supposed to find out. Now the next part is to find out, to evaluate the circuit when the fault occurs. Okay, so this is with fault or during fault. Second step, during fault. Now during fault, we'll draw the equivalent circuit. Okay, let's see now what we have. Okay, so the question says that the fault occurs somewhere in the middle of the second line. So when it occurs in the middle of the second line, the impedance is split into two. Now you can take any two values, but make sure that the values correspond to the fault occurring somewhere in the middle. So because the word middle is used, I am going to split this 0.6 into 0.3, 0.3. Please observe. Here's our infinite bus, 1 pu, and this is 0.2, this is 1 pu, and here we have J.6. Okay, so the fault has occurred somewhere in between, in the middle of the second line. So I have split this impedance into two parts. So here we have 0.3 and here we have 0.3. You can consider it as 0.2 and 0.4 if you like, or 0.25 and 0.35, any way that actually adds up to 0.6. But make sure that it is not too much of a difference, because the question says that it happens somewhere in the middle. Okay, so now we have a few things to do. This is in the form of delta. You will see that it is in delta form. So first we have to convert it into star form, a star connection, and then convert it back into delta in order to form a pi connection. We'll do it step by step. Okay, so the first thing is to evaluate this portion here and convert it to star connection. So we are trying to resolve this entire thing as much as possible. So the first step is to convert this into star connection. So in order to do that, you will have to recall the basic formulas of conversion of delta to star and then star to delta. I'll put it down here. Okay. So I'm going to note this down in the general delta shape. Okay, so we have 0.6, we have 0.3, we have 0.3. So this is the general delta shape. I've just converted that part, taken only the part that we need to convert. Okay, and we need to convert this into star form. Okay, let's call this R1, R2 and R3, and correspondingly here we would have, this is RA, this would be RB, and this would be RC. So we know the conversion formulas. The formula is R1 is equal to RB RC divided by RA plus RB plus RC. Similarly, R2 would be RB RA divided by RA plus RB plus RC, and R3 would be RA RC divided by RA plus RB plus RC. Okay, so we have our values here and we can calculate what R1, R2, R3 is. Plug in the values. You will find that R1 is 0.15, R2 is also 0.15 and R3 is 0.075. Okay, so if we were to write this in the equivalent form in the circuit, please observe. Okay, so we are converting this delta connection to star. So this is what we get here. That's 1, 2 and 3. That's our infinite bus 1 pu, and that's 0.2, j.2, that's 1 pu. Okay, so this is our star of what we have converted. So here we have R1 at j.15, and then we have R2 which is also j.15, and here we have R3 at j.075. Alright, so now these two impedances are in series, so we can just add them to give us one value. So this is what we get now. This is 1 pu, this is j.075, this is 0.15, and here this is 0.2 plus 0.15, that's j.35, and here we have 1 pu. Okay, so from here this is what we have. Now you will notice that we have a star connected form here with 3 impedances. Now we cannot solve this because we have one impedance here which is connected to the infinite bus, and we have one which is grounded and one here which is connected to the source. So the next step is to convert this into pi form or back to star, back to delta. So this entire thing, converting it back to delta form. So basically we need the form in like so. We have one here and then one here, one here. So this is 1 pu, this is 1 pu. We need it this way. This is because when a fault occurs, the second line would be grounded immediately. So the remaining impedance is what we have to calculate, the maximum power that passes through that particular point. So since we don't have that in the first equivalent circuit, we have to try and resolve it as much as possible in order to get it into pi form. That's the ultimate aim here. Alright, so we need the values of these 3 impedances. Let's call this as RA, this as RB, and this as RC, and the values of the above circuit as R1, R2 and R3. So we are converting that into this using this formula right here. So you know how to do it when it is from delta to star transformation, but now we'll have to do it from star to delta transformation. So star to delta, I'll write down one formula, you can do the rest. RA would be R1 R2 plus R2 R3 plus R3 R1 divided by R1. So RB would be R1 R2 plus R2 R3 plus R3 R1 divided by R2, and RC would be, the numerator would be same, divided by R3. Okay, so that's basically the formula. Once we have this formula, we can substitute the values from the previous equivalent circuit here. R1 is 0.35, R2 is 0.15 and R3 is 0.075. So we'll have the values of RA, RB and RC. So let me just flip this over and work it out here. Okay, so now the values of RA, RB and RC according to the formula and the previous equivalent circuit that I've noted down. RA is 0.257. I will leave the substitution and the working out to you. I'm giving you the values so that you can work it out and check. So RA is 0.257, RB is 0.6 and RC is 1.2. So our circuit now becomes as such. let me just show you. We have so here this is one PU, this is one PU, this is one J1.2, this is J.6 and this is J.257. Alright, so now we concentrate on the impedance here of the line. So the power at fault condition, at faulted condition, okay, at faulted condition would be equal to V square, that's 1 square divided by 1.2, and that results in 0.833. Now we can find out what the value of the ratio is. The ratio in the question, as we started off with, it is P at pre-fault divided by P at faulted condition. So that's 2 divided by 0.833, which comes to 2.4. So 2.4 is the final answer for this question. 2.4. Well, I hope this has helped.
Thank you for watching this video. For future videos, please click here to subscribe YouTube channel. Visit our site thesis123.com for free student project or research ideas and online training. Follow us Facebook, Twitter, Google+ and Pinterest.